everyone, this is a quick little proof run through of the Neyman-Pearson lemma. This is going to be the version of the lemma I'm going to be working with. There are a couple other versions out there, so you can probably generalize this to the one that you're looking at. But for this lemma, what is basically going on is for a set of simple hypotheses, where H is our null hypothesis and A represents our alternative hypothesis. If we have a test of this structure, and recall that this is the situation in which the test is rejected, this first one up here. So if we have a test of this structure and the type 1 error rate is equal to alpha, then that test is going to be the uniformly most powerful test. Now recall this is our power function, and I've written it a couple of different ways over here, mostly as a reminder to my future self. So we're assuming that both of these conditions hold for a particular test. We're going to call it phi. And what we want to show is, we want to show that a test under these conditions is uniformly most powerful. That means for any and all other test phi of x that are level alpha, we have the power function of phi of x, not phi of x, theta 1, so theta under the alternative hypothesis, is going to be greater than or equal to phi star theta 1. Now, this is coming from the definition of what it means to be uniformly most powerful, but because we only have a simple set of hypotheses, we only have to check this one value. If we had a more complex set of hypotheses, we would have to do this for all theta naught within the set under the alternative hypothesis. So we only have to check this one value though, that's all we need to do. Now, recall what it means to be a level alpha test. That means, so a level alpha is when the power function phi star under the null hypothesis is less than or equal to alpha. Now, part of our condition is that we have a test phi, not phi star, is going to be size alpha, which means it's exactly equal to. This is going to come up in the proof. So going to proof, we first want to notice, or just call attention to, that phi star of x is always going to be between 0 and 1. And with this fact, and the fact that the arbitrary test we picked is level alpha and the test under the given conditions is size alpha, we note that phi of x minus phi star of x times f of x given theta 1 minus k times f of x given theta naught is going to be greater than 0. Why is this the case? Because if phi of x given theta 1 is greater than k f of x given theta naught, then phi of x is equal to 1. And if it's less than, if phi of x given theta naught is less than k times f of x given theta naught, then phi of x is going to be equal to 0. This is going to be negative, and we have a negative value here. So we know that this guy is always going to be positive. From that, we can see that the integral over all of x for this. Just go ahead and copy paste. Oops. That integral is also always going to be positive. Now this is the integral over all values of x. Oh, it's really a gigantic integral, but we're going to simplify it this way. We can expand this integral out to see phi of x, integral of x, phi of x, f of x given theta 1 dx plus integral of x, phi of x times k. So this would be a minus sign, f of x theta naught dx, and then we would distribute again, negative integral of x, phi star of x times f of x given theta naught, or theta 1 dx. And then we have plus k times the integral of x, phi star of x, f of x given theta naught dx. Now these integrals are just another way to define our power function. So this becomes 0, and this is the power function of phi given theta 1. Our second term here is going to be minus k times the power function of phi given theta naught. Our next component is going to be minus, and we have the power function phi star given theta 1. Then we have plus k times the power function phi star given theta naught. We can rewrite these terms. We have b, or the power function of phi theta 1, minus the power function of phi star theta 1. So I use this component and this component. And then what I'm going to do is I'm going to pull out a negative k. Power function of phi theta naught minus the power function of phi star theta naught. Now, we know that the power function of phi, given the null hypothesis is true, is going to be alpha. And we know that the power function of phi star, given the null hypothesis true, is going to be strictly less than alpha. So this component in the parentheses is going to be greater than or equal to 0. And since we have a negative k out here, we know the whole component, including the negative k, is going to be less than or equal to 0. This implies that we have this component is going to be greater than or equal to 0 by itself, which further implies that b, or the power function of phi star given theta 1, is going to be greater than or equal to the power function of phi theta 1, which is what we desired. So that's it.